Well, hi guys. We're going to do area inside of polar graphs today, and we're going to do a couple examples. And the formula we're going to be using for area polar graphs is the integral from a to b of 1/2 r squared d theta, where r is the equation as a function of theta of your polar graph, and a to b are your angles that we are going to integrate between. So let's do an example of a fairly easy example. Let's consider the graph of r equals cosine of 2 theta. Now, from pre-cal, you should know that this is a 4-petaled rose, and let's find the area inside one of those petals. So let's go take a look at a picture on a calculator, and then let's talk about how we're going to do this. Most importantly, the angles we're going to go between. So let's go take a look at this thing. Here's our 4-petaled rose, and I've got it graphed here, and we want the area inside one full petal. And what we really want to know is what angles do I go between that will generate this one full petal. So if I were to hit trace, let's take a look at this first dot here. You can see the first dot has a radius of 1. That is because the first angle, theta equals 0. 2 times 0 is 0, and the cosine of 0 is 1. So this first radial line has a length of 1. Then as I trace through this, I'm tracing the... Oh, I just need to go to the right, sorry. I'm tracing through this, and you can see my radial lines are getting smaller. That's because as theta increases bigger than 0, it's going to make your angle get smaller until we get to the pole. Your angle won't get smaller, your radial line will get smaller. And we want to, until we get here, and then we actually have a radius of 0, we can figure that out. So what I'm going to do here is I'm going to take advantage of some symmetry. I'm going to figure out how long in theta angles does it take to get from the starting point back here to 0. And I'm going to show you how that is being swept out, and I'm going to show you my approach to this. By the way, this theta of 0.78531, and if you know what pi is 3.14159.265. Ask Mary, she knows it a lot further than I do. We might be able to figure out why that angle is what it is. So let's head back here and do some math on a sheet of paper. What I've got is a polar curve. Get to my pen, and I've got this one petal I'm looking at. It started graphing like that and went to there. So what I'm going to do is I'm going to find the area of the whole petal. By the way, it doesn't graph it like this. It actually graphs it weird. At this point, it comes down here, and then it does this, and then it comes up here and does this. It graphs it sort of funky. Boy, I sure can't graph like the 89, can I? Wow. Well, anyway, so what I'm going to do is I'm going to take these first sets of radial lines here, and I'm going to find the angle that makes these radial lines get back to 0, and I'm going to take that area and I'm just going to double it. And so what I need to know is, what is this angle right here? So I need to find out, when does cosine of 2 theta get back to 0? When does it get to the pole? When does it have a radius of 0? You're going to be happy that I actually made some computer generated pictures later, because that's really a sad looking flower. If I were to give that to a woman, unless I was in kindergarten or she was my mom, that would be a sad day for me romantically. Alright, so what I'm going to do is I need to figure out, well, the cosine of what is 0? Well, the first angle that cosine has a value of 0 is pi over 2. So I'm going to let 2 theta be equal to pi over 2. So this first angle is going to be pi over 4, which is, if you call pi 3, just to estimate, 3/4 is about 0.75, and that's about the decimal that we were at before. So this should make sense. So what I'm going to do is I'm going to take and integrate between 0 and pi over 4 of 1/2 r squared d theta. But that's just going to be this upper half of this petal. So I'm just going to double that, and that will be the area inside one loop. And of course the 1/2 can come out in front of the integral, and I can just do the integral from 0 to pi over 4 of cosine of 2 theta squared d theta. So what I'm going to do on my calculator is I'm just going to go to the home screen and I'm going to use x's instead of thetas, and I'll ask my calculator to give me that value. And unfortunately, when you're graphing in polar mode, it won't integrate for you. It'd be really cool to see that picture and like fill in the area like it's filled in integrals before, but it won't do that in polar mode, which makes me a little sad. But that's the setup. Let's go take a look at another example. What about the area of the inner loop of 2 plus 4 cosine theta? Now, whenever you have a plus b cosine theta, you might not remember this from pre-cal, but if a and b are the same, like 2 plus 2 cosine theta, it makes like a heart. But if b is larger, you create an inner loop. So let's go take a look at that picture, 2 plus 4 cosine theta. Got that stored in my calculator here. I'll turn that first one off and turn the second one on. Let's take a look at this graph, and I probably need to look a little further out to the right. Cosine theta, by the way, heads right and left. X max of, let's do a 6. And let's do an x minimum of, well, negative 2 is probably good enough. So let's go down here and change my y minimum down to about negative 3 and y maximum up to about 3. I didn't quite see far enough up and down, but you're going to get the picture from that. Alright, so what I want is I want the area inside the inner loop. And so what I need to do is figure out, when does this graph get to that inner loop? Now, for those of you that did your homework yesterday, you're going to appreciate now why the book asks you to find the interval for theta that will allow you to completely sweep out this graph. If I hit trace, I'm way out here at 6, and that should make sense because if I plug in 0 for theta, the cosine of 0 is 1, times 4 is 4, plus 2, so my first radial line is way out here at 6. And so what this graph is doing is it's sweeping out, it'll start as we trace this, it's sweeping out that what's called the outer loop. And what I really want to know is, what angle for theta does it come down here back to the origin and start sweeping out the little loop, the inside loop? So that's what I'm going to have to figure out on, when does the graph get back to the pole, or when does r equal 0 for those two times? I want to find those two angles that it created. So I've got a picture of that back here, and it's a much better picture than what we saw before. So let's get my pen out here. Let's go forward and see what happened here. We set the r equal to 0 so we can find the two times that it was back at the origin, so we can find those angles, and those are our a and b angles. Of course, you can subtract 2 from both sides, divide by 4, and you get cosine of theta is negative 1/2, and that happens at those two angles. That was the same thing on our video from our first video for polar. One was cosine negative 1/2, these two angles. I guess I'm biased to that. I don't know. Anyway, let's take a look at this picture. So here's what we want to find. Now, when this graph was first being swept out, it was sweeping out this area of the little circle. That's not really a circle, the little loop, plus the big loop. So I really didn't want these angles for theta at all, because those angles were including all of this area in here. But what happened as theta eventually came down to 2 pi over 3, when it got here to 2 pi over 3, then it started sweeping out the area of this little loop. And that's what I want. I want it just sweeping out that little area. And that happens from 2 pi over 3 to 4 pi over 3. And that's how we found that with setting that equal to 0. So from 2 pi over 3 all the way around to 4 pi over 3, that's when it sweeps out just that little inner loop. So that gives us our a to b. So the setup of our area is going to be the integral from 2 pi over 3 to 4 pi over 3 of 1/2 r squared d theta. And you can, again, from the home screen, you just want to put that in, use x's and do the integral of 1/2 of 2 plus 4 cosine x squared from 2 pi over 3 to 4 pi over 3, and that's how you would actually get the answer. Sometimes these are just setups, though, on the AP exam. You don't actually have to type them in. Now, what if, this is the hardest part, what if we get two polar curves and one of them is carving, a piece out from the other one? And that's going to happen if they decide to be mean on the AP exam. It's a harder question, but let's take a look at it anyway. If we have graph that's carving out from another graph, we're going to do a subtraction process. Just as this is all this is the washer method being applied. So let's take a look at one example for that. What about the area that lies inside a graph of 3 plus 2 sine theta, but outside r equals 2? Let's go take a look at what that would even look like. Go back to my y equals. I'll turn that off, and I'll turn these two on. Okay, and I'm going to have to look further up in the y-axis. If you just have sine theta in your polar curve, it goes up and down. So I need to see further left and also further up. Let's go up to 6. That should be plenty. Take a look at the graph. So what I want is an area that is inside this big graph but outside the small loop, and I'm ignoring this stuff down here. So I need that. I've got this also sketched with the computer and not with my poor graphing skills with my little air slate. So that's what we're after. That's sort of an interesting picture. Inside that 3 plus 2 sine theta, but outside r equals 2. So let's go take a look at that. Here's what I want, this area in blue. And what I need to find is where these two graphs intersect each other. Where does 3 plus sine of 2 theta equal 2? I don't know if there we go. All right, so I can subtract 3 from both sides. And so where does sine of theta equal negative 1/2? And so I want to know what angle for theta creates that. And I've got this on this next paper here. That happens at 7 power 6 and 11 power 6. But here's something that we have to be careful of. This is what makes this difficult. If we plan on going from 7 power 6 to 11 power 6, we will be sweeping out this area right here. And that is not what I want. I don't want to start with 7 power 6 and get to 11 power 6. That's not what I want. So let's erase that. That would give us the area in these 3 small sections here, or these lower sections. What I want is this area in blue. So instead of going from 7 power 6 to 11 power 6, we're going to sweep out from negative power 6 all the way out to 7 power 6. I want to start down here and sweep this area out, and that will give me that area in blue if I subtract off the area from the circle. So I want to go this way. So my integral is going to be from negative power 6 all the way out until we get to 7 power 6. And what we'll do is we'll subtract out the area of that circle. So here's why this answer looks like this. We go from negative power 6 to 7 power 6. The outside radius squared is that the bigger circle minus the smaller circle squared. And again, you could, from your home screen, you could type that in using x's.